In the second part of this video on generics, we will examine how to create both generic interfaces and methods, and we will provide examples for both. We begin with generic interfaces. The syntax for declaring generic interfaces is similar to generic classes. Here is the syntax rule. Notice that, like with generic classes, a generic type parameter is placed after the interface name, and it is enclosed in corner brackets. The same lexical convention applies, which is using a single uppercase letter for the generic type parameter. The syntax for instantiating generic interfaces is similar to what we saw for generic classes as well. And here is that syntax rule. The generic type argument follows the interface name, and again, it is enclosed in corner brackets. This interface, stack interface, is an example of a generic interface. Recall that defining an interface allows different implementations to be interchanged. We will see a second implementation of this interface later when we come to linked lists. Notice that after the interface name we place the generic type parameter t in corner brackets. Next, we consider the class ArrayStack that implements this interface. The generic type parameter t must follow both the class name and the interface name. Aside from the first line of this class, the remainder is identical to the generic stack class that we examined previously, as we can see scrolling down to the last method in the class. We now consider generic methods. In addition to making whole classes and interfaces generic, individual methods can be generic as well. Not surprisingly, the syntax shares some similarity to the other two cases. As before, the generic type parameter must be included, and it must be placed in corner brackets. It must be placed before the return type in the method's signature. Here is the signature of the generic method concatenate that we will examine shortly. When we make an individual method generic, it is usually because one of the parameters is of the generic type. Note that in the above example, the type of the elements of the parameter array are of the generic type t. This class concatenate contains the method concatenate, which is the generic method whose signature we just encountered. Here is that method's signature. Notice the placement of the generic type parameter before the return type. The string result is initialized to the null string. Then a for each style loop is used to iterate across the entire array. Each element is concatenated onto the end of the string result together with a space that separates them. Notice that the type of the element is the generic type t. Also recall that when any object is concatenated onto a string, the toString method of the appropriate class is implicitly called. Notice that this method can be used to concatenate a list of integers or a list of strings. First we define an array of integers and then call concatenate and display what it returns. Unlike classes, generic methods do not require explicit instantiation. The generic type is inferred from the type of the argument passed to the method. Next, we repeat the same process using a list of strings. In fact, an array of any kind of object could be used. Next, let's run this program. Notice that the strings containing both arrays are displayed. Our final topic on generics is bounded types. Bounded types allow a generic type parameter to be constrained to a subtype of another type. By using a bounded type, the compiler can assume that the methods available in the bounding type will be available with the actual type when the generic is instantiated. Here is the syntax. Notice that following the generic type parameter is the reserved word extends and then the name of the bounding base type. Although the syntax uses extends rather than implements, the base type is most often an interface rather than a class. Here is the signature of the method isSorted that we will examine next. Notice that the signature specified comparable as the bounding type. Consequently, this method can only be instantiated for types that implement the comparable interface. In other words, types that contain a compare_to method. This class checkSorted contains the generic method isSorted. Here is its signature. As we just observed, the parameter of the method is a bounded type, which must implement the comparable interface. This for loop compares adjacent elements, ensuring each one is less than or equal to the next. Notice that the compare_to method is needed, which is why a bounded type is required. Because both integers and strings implement comparable, this method can check both kinds of lists to determine whether they are in sorted order, which is exactly what the main method of this class does. First, two arrays of type integer are declared and initialized, and then the isSorted method is called with each of them. Next, two arrays of strings are declared and initialized, and then the isSorted method is called with each of them. Next, let's run this program. We see that true is displayed for the arrays sorted1 and sorted2, and false is displayed for the arrays unsorted1 and unsorted2. Next, let's try removing the bounding restriction. Notice the compilation error that occurs.